Some cosmic questions are rigged to resist a final answer. The immediate takeaway is simple. Our universe hides information behind limits. Point a telescope into deep night and distance pushes back. Zoom in with equations and uncertainty thickens like fog. By no final answer, I mean not even in principle, not with bigger telescopes, faster chips, or smarter theories. Nature draws boundaries we cannot cross without breaking its rules. This isn't a failure of science, it's part of the map. In that map, some edges are cliffs, not doors. Today we visit those cliffs and see why they exist. You'll leave knowing where curiosity stops and wisdom starts. Stand on a dark hillside and picture a glowing bubble overhead. That bubble has a real name, the cosmic horizon. It is the farthest distance light could ever have reached us. Why care about a boundary painted across empty space? Because anything beyond it can never influence us, not ever. Space itself expands, carrying distant galaxies away from our light cones. Beyond a certain distance, recession outruns any photon chasing home. No trick dodges this because it is geometry, not speed limits. Light from there stretches into wavelengths our instruments cannot detect. Even worse, that region can never send a fresh signal. Think of waves on a river pulled downstream faster than they paddle. Galaxies beyond the horizon are those drowning waves, forever downstream. Here is the concrete scale. Our observable radius is about 46 billion light-years. The universe is 13.8 billion years old, but expansion changed distances. We see the cosmic microwave background from 380,000 years after the Big Bang. Its glow arrives as microwaves, stretched by expansion into a near-perfect blackbody. Everything farther lies outside our particle horizon, hidden by spacetime itself. Accelerated expansion adds another wall, a future event horizon. Signals we send now will never reach most galaxies we can see. No future detector, however godlike, can reverse that separation. Rule of thumb: if expansion wins, information loses. Astronomers still map what we can, across surveys and wavelengths. They stitch a bubble's worth of reality, precise yet incomplete. Bottom line, a horizon makes beyond a story, not a measurement. Open a sky map and you see mottled speckles of ancient light. That speckle pattern is a lottery we drew only once. Cosmic variance means some measurements have unavoidable statistical noise. We care because this noise sets a hard floor on certainty. More data helps small scales, but the biggest modes are unique. There is only one sky at the largest angular sizes. No reruns exist to average over, reduce noise, or confirm anomalies. The math is clear: fewer independent modes mean bigger fractional uncertainty. Large multipoles, like the quadrupole, have just a handful of samples. That scarcity bakes doubt into any claimed weirdness on giant scales. Example: in real terms, the CMB quadrupole power looks unusually low. Planck mapped it beautifully, yet its oddity sits near 2 sigma. 2 sigma is interesting, but it is also common by chance. We cannot observe another universe to see if it repeats. No upgrade fixes that, not even a perfect noiseless detector. You can sharpen beams, deepen exposures, and still hit this wall. Surveys like Daisy, Euclid, and Rubin expand maps with stunning detail. They crush noise on small scales, while giants keep their shrug. Theory leans Bayesian here, combining data with priors to steer inference. The result is robust, but it always carries irreducible spread. One sentence recap: some cosmic dice were rolled once and stay rolled. Scientists embrace that floor and design questions that clear it. Net result: precision has a ceiling when the sample count is 1. Picture the Big Bang as foam, then quickly as calm glass. That shift hides a barrier called the Planck wall. It marks scales where quantum gravity must shape spacetime. We care because before that wall may stay forever undecidable. Did a bounce happen or a true beginning? Did dimensions change or fields tunnel through a landscape? Our best tools stall because required energies are absurdly high. The Planck energy is about 10 to the power of 19 GeV. The LHC reaches around 10 to the power of 4 GeV. That gap is roughly 10 to the power of 15 in scale. No civilization builds an accelerator that bridges that canyon. Nature could help through relics imprinted on cosmic backgrounds. Inflation, if real, smooths space and erases most initial fingerprints. That smoothing is a gift for simplicity and a curse for archaeology. Some models add primordial gravitational waves with a B-mode curl. We hunt them in polarized microwaves, faint as whispers in snow. A detection would reveal energy scales, yet not the full story. Different early scenarios can mimic the same B-mode strength. Even with a signal, many detailed histories would fit. Rule of thumb, beyond the Planck wall, uniqueness dissolves. So we aim for what is decidable, like energy bounds. Bottom line, before smooth, may stay poetic, not provable. Snap to the far future and ask how the cosmos ends. Dark energy is the driver that decides expansion's long game. It is a smooth energy density that accelerates spacetime's growth. We care because its behavior decides heat death, rip, or remake. Physicists summarize behavior with one number, the equation of state W. If W equals -1, space inflates gently forever. If W drifts, the future bends to a different script. We probe W using standard candles, standard rulers, and relic light. Type Ia supernovae map distances across billions of light years. Baryon acoustic peaks set a ruler inside galaxy clustering. The microwave background anchors geometry at the last scattering surface. Each probe has systematics, degeneracies, and a cosmic variance floor. Subtle dust, evolution, and calibration can tilt inferred distances. Nonlinear growth and neutrinos blur clean parameter lines in fits. Combine everything, and you still live with model dependence. Today, best fits sit near -1, within a few percent. Tomorrow's surveys will squeeze error bars, maybe by another factor too. Yet no measurement can prove exact equality to infinite precision. Different lingering systematics can masquerade as tiny W departures, and if W changes slowly with time, simple models may mislead. Common mistake is thinking tighter error bars erase all ambiguity. They crush noise while assumptions still steer the conclusion. Net result, we may never nail destiny beyond a narrow band. Now drift toward a black hole, past quiet stars and dust. An event horizon is a surface that traps all future signals. We care because interiors could settle deep questions about gravity. Inside, spacetime is so warped that every path falls inward. No photon or particle can climb back to report conditions. That one-way rule holds, unless physics itself breaks at extremes. From outside, we infer mass, spin, and charge, not the furniture. Different interiors can share the same exterior by design. Gravitational waves let us hear mergers ring like struck bells. Those ringdowns test geometry, but not detailed microstates inside. Some theories predict subtle echoes, reflections near the horizon. Searches push limits, yet nothing conclusive has appeared so far. Event horizon images show glowing gas, not the hidden chamber. M87 looks like a donut, with darkness where light cannot orbit. That darkness is not a photo of the interior, just its shadow. Common mistake is picturing a camera flying out afterward. There is no afterward for outbound cameras, only inward time. Example, in real terms, two theories can match one ringdown. Choosing between them needs clues that horizons refuse to share. Bottom line, black holes guard answers behind a perfect silence. Scan the radio spectrum, and it mostly hisses with natural noise. The puzzle is famous, intelligent life feels plausible yet unseen. The Fermi question asks where everybody is, given cosmic time. We care because the answer rewrites our future and our ethics. Signals fade with distance, scatter in plasma, and drift in frequency. Beams are narrow, lifetimes are finite, and languages mutate. Technologies pivot, leaving few overlapping windows between us and them. Stars flare, planets hide, and our instruments trade depth for breadth. The search space is absurdly large across sky, time, and channels. Common mistake is equating no detection with a cosmic no. Absence of evidence is shaky when coverage is microscopic. Example, in real terms, our radio search volume is tiny. One estimate compares it to a swimming pool within all oceans. We have not checked the seafloor or even most coastlines. Biosignatures are coming, methane and oxygen mixes on exoplanets. Even then, chemistry can mimic life and clouds can trick. A single detection would answer alone, instantly with a no. But a null result may never reach finality, even in centuries. Search anyway because the payoff justifies the patience. Net result alone could stay undecidable while progress still explodes. Open a physics handbook and you meet numbers with personalities. Constants of nature are fixed values baked into our equations. We care because their origins hint at deeper layers of law. Our best theories treat many constants as inputs, not outputs. Change them slightly and stars or chemistry can fail outright. Some frameworks predict families of possibilities, a vast landscape. Selection effects then say we arise only where life can. That story explains where we are without deriving why these. It trades proof for survivorship logic that resists direct tests. Take the cosmological constant, vacuum energy driving cosmic acceleration. In Planck units, it is about 10 to the power of minus 122. That freakish smallness shocked everyone and still defies derivation. Weinberg argued values much larger would crush early galaxy formation, so observers would never arise to ask about larger values. That is persuasive, yet it leaves many models equally viable. The fine structure constant sets electromagnetic strength near 1/137. Tiny shifts change nuclear resonances and alter carbon production in stars. Can a future theory compute these from first principles? Maybe, but it might instead compute a menu, not a unique meal. Bottom line, why these numbers may keep one foot in philosophy. We started with a blunt truth: some questions are rigged against finality. The tour showed horizons, variance, walls, and one-way doors. That mix is not defeat, it is the shape of knowledge. Science shines where answers are provisional, testable, and honest about edges. The trick is asking decidable versions while respecting undecidable cores. Quick mental image, a map with cliffs and bright trails along them. We walk those trails and still see farther every decade. Keep your curiosity sharp and your conclusions soft. If this helped you breathe easier about uncertainty, consider subscribing for more. Bottom line, limits can guide wonder without dimming its light.